Hello, everybody. So last week I was on leave, so we could not have this live session. Okay, so but anyway, we are into chapter 5, so we just finished it, and here we are going to solve tutorial problems from chapter 5. Okay, so as you know, this was about the we had first order system, second order system. We found out the response, impulse response, unit response, uh, ramp response, etc. And we also looked at the Routh's stability criterion. Okay, so any question on this, on these topics? Any question, guys? Okay, so if there is no question, so let's start with the tutorial problem solving, and we will look at chapter 5. Yeah, so this is chapter number 5, and tutorial problems have been shared with you already, so we will go through this. So we have the chapter 5. Okay, so B5, and then we have 1, 2, 5, 8, 13, 20, 21, 23, 24, 26. So as usual, we will not completely solve the problem, but we will follow the procedure, basically the steps we will discuss about. Okay, rest details you can work out. So you are supposed to solve on your own, but here the idea is just we will discuss the procedure for solving this. Okay, so let's look at B51. Okay, so B51. Yeah, start with that. So let's see what the problem is. The problem goes like this. It says there is a thermometer requires 1 minute to indicate 98% of the response. Okay, so 1 minute, so that means 60 seconds, that for 98%. Okay, sorry, 98%. 98% of the response to a unit step input, assuming the thermometer to be a first order system, find the time constant. So first of all, first order system, how you define the first order system? And you know that simply the for the transfer function, GS is given by 1 over, and then you have TS plus 1. Okay, and this is a time constant T, where T is the T equal to time constant. It's a time constant. Okay, or you also write 1 over T over S plus 1 over T here. So we also write this as well, right? Okay, now if first order system is given by this one, and then we have to find out the response, how the response is. Okay, and what is the response? So response due to unit step. Yeah? Okay, now if this is the unit step function like this, and the response goes something like this one for first order system, and how exactly you can find out. How you find out? So typically you say CT over, or rather we write CS over RS, or is equal to, in this case, equal to 1 over TS plus 1. Yeah, or CS equal to RS multiplied by 1 over TS plus 1. Yeah, and this is unit step function. So RT is equal to 1, or you can say UT, it's unit step function, and hence this you take the Laplace transform of that, and that becomes RS equal to simply 1 over S. Yeah, so we know that in that case that CS equal to RS is 1 over S and 1 over TS plus 1, right? And then you can you take the in now a CT will be equal to Laplace inverse and then 1 over S TS plus 1, right? Okay, and which will be equal to which is equal to, we can forward, so L inverse, and we will have 1 over S plus B over TS plus 1. So we simplify, so it is equal to this is where we know that in this case A TS plus 1 plus B S is equal to, if you look at this side, should be equal to 1. So equal to 1, or simply we have A, right? A times T plus B S plus A equal to 1. Okay, that's what we get. So we get A times T times S plus B times S, so AT plus B times S plus A times A here. So from here we can see that simply A has equal to 1 and the AT plus B equal to 0, and this gives us simply B equal to minus A times T, and since A is equal to 1, so we get B equal to minus T, and hence we get CT is equal to simply L inverse, and A is equal to 1, so we get 1 over S, and B equal to minus T, so minus T over TS plus 1. Right? So we get like this one, and you know, take Laplace inverse Laplace transform, and this one is nothing but unit step function, so you get UT minus, and value of this will be simply you get just e to the power. So this t you can divide here. So this becomes, this divided by here. So this becomes s, and this 1 over t here. So 1 over s plus a, you know that is e minus t over a. So basically what we get in simply is e to the power minus t over t, this big T. So this is the, or simply 1 minus e to the power minus t, because this is unit step function. So this ut is nothing but 1 for t equal greater than 0. Yeah. So you get that. So now what it says that it reaches. So the problem says that a thermometer requires 1 minute to indicate 98% of the response to a. So that means our graph for this goes like this. Yeah. So here, so if so 98%. So let us say this is the actual 1, from here to here it's 1, and this is 98%. And for this time is equal to 1 minute, or this is the 1 minute. Yeah, this is 1 minute. So like this one. So that really means that our CT, which is equal to 1 minus e to the power minus t over t, we know that this CT is 0.98 is equal to 1 minus e minus t is equal to, you can have in minute also. So t, we can write a t equal to 1 over t, like this one. Yeah. So we get the e to the 1 over t is equal to 1 minus 0.98. Yeah. And is equal to 0.02. And we take natural log 1 minus 1 over t is equal to, this becomes 0 ln of 0.02, and it is minus 1 over t is equal to ln 0.02, and hence we get t equal to simply minus 1 divided by ln 0.02. So this you will get in minutes. Yeah, so this is how the answer will be. Yeah, so although we actually solve it fully, but just to show basically the how the formula that you learn, those can be applied, and but be careful, you try to solve the whole, not memorize the equation, because equations you don't will not understand where it in what case it will be applicable. Okay, the second part is, if the thermometer is placed in a bath, the temperature of which is changing linearly at the rate of 10, so d temperature is changing. So what is changing? So this is a function of t, so response, right? Okay, so the r input is changing, so dr over dt, this is changing at the rate of 10 degree per minute, right? How much error does the thermometer show, right? Okay, so that really means this is the ramp basically. This is the ramp, and then dr over dt is given. This is how it is changing. Then is finding out how much is the error in thermometer. So error equal to what? So how to solve it? Okay, so your equation, you know that CT over RT. Yeah. So first looking at the statement, you have to actually see what exactly is being asked. So CT over RT, as you know that this is the C, this is RT, and this is the CT, and this is a first order system given 1 over TS plus 1. So this is how it is given. So where this is the body temperature here, and this is the indicator, right? So whatever the value here is, this will be the indicator which will be showing it, and in between there is a sensor circuit. Yeah. So if this itself is rising, so then error will be what? Error is basically, we are talking about error, right? So ET is equal to nothing but actual the CT minus RT. Yeah, CT minus RT. Or this is basically the like this. Yeah. So if you have to find from the reference how much is the error, that's you want to find out. So how to find out? So we know in this case dr over dt is going like this, right? So we have dr over dt given there. Okay, and now so this is the ramp basically. So this is how the ramp is. Yeah. Okay. So basically the our input is what? How is our input changing? So our rate is given, or we take this one. So see here. So R dot is equal to 10 degree per minute, let us say. Let's assume minute is our unit. Okay, so we don't need to actually change it to second. It's fine because our time constant is also in terms of minute only, so it's okay. So now if we take a Laplace transform of this, then what happens? So we take it will be S, and then we will be RS. Right? So R dot so equal to S RS minus R0, right? So this is the RAM, so it is okay. Will be equal to 10 only. Yeah, so simply we have RS is equal to 10 over S. Okay. 10 over S Okay, so this one is 1 over S. Sorry, this will be 1 over S. So it's okay. So we have S here, R dot. If we take a Laplace transform both the sides, right? So we are going like taking like this one. So this one, you know that whenever there is a derivative, so what you get in this case is S times Rs minus R0 equal to, and this is a simply this is a step, unit step, right? So for unit step, you have 1 over S. So what you get, Rs equal to 10 over S square. So now given Rs equal to 10 over S square, you have to find out the error. Yeah. So Rs is equal to this. Okay. And now you know that Cs over Rs is nothing but the GS, which is equal to 1 over TS plus 1, we know already. And hence CS is equal to 1 over TS plus 1 multiplied by RS. And where RS, as you know, is equal to 10 over S square. And then you have 1 over TS plus 1. Okay, so this is a CS, yeah. Okay, and one way of finding out the steady state error, it says how much error does the thermometer show. One way to show is you find out the CT equal to L inverse of CS, and then you take L inverse of 10 over S square plus TS plus 1. So we can do that. And then your error is nothing but is equal to CT minus RT. Yeah, and where RT is simply is equal to whatever those CT is, a minus R is changing. It's a ramp, right? 10 degree per CT. Here this should be minus CT minus RT. Okay, this is not equal to, was minus. Okay, now. So this is CT. Okay, the CT value you will get whatever value you will be getting here, and RT, you know, this is a ramp. This is a 10 times T basically. This is the value, right? 10 times T, and this will give you the error. Yeah, you can also find out the steady state error, and the ESS in this case is equal to, you know that this will be error CT. The CT minus RT, right? And the limits T tends to infinity. So at T equal to infinity, it can find what is the error actually, and which is equal to simply error ES times S limit S tend to 0. As we know that, so in the lecture it will be covered. So here we this also comes from the final value theorem. This is final value theorem, and it says that for any function ft, limit tend to infinity is equal to limit s tend to 0 f of s multiplied by s. So this is the final value theorem, provided, of course, ft is bounded, right? So ft is bounded, or this is a finite value, right? So this. Okay, so this we can straightaway we can apply, and in this case we get error or ESS steady state error equal to limit s tend to 0, and then we have s multiplied by r CS minus RS, and we are equal to limit s tend to 0, and we have s, and CS is, we have already CS. So this is the CS, right? So 10 over s square. So we have 10 10 over s square, then ts plus 1. So this is our s minus rs. Okay, this is cs, was this one, and then we have rs, and rs is, what is rs? So rs is okay, from here you can find out. So rs is this. rs is 10 over s square. So we have 10 over s square. So 10 over s square. Right? Okay. So okay. So so what we get in this case is limit okay. rs is given and cs is here, for ts plus 1, and then we are going to find out this. Okay. Okay, now let's do it. Okay, so limit s tend to 0, so equal to limit s tend to 0, and then we have 10 over s square. So let's have 10 over s square, that's common, so it comes like this, 10 over s square, 10 s square, and then we have 1 minus ts plus 1. So here we go, 1 minus ts minus 1 over ts plus 1. Right, so we have 10 s square, so we have 1 minus ts minus 1 by ts plus 1. Yeah, so we get like this. Okay, so we have that is equal to, and then we will have limit s tend to 0, and then we have here, so this cancels out, so we have ts, and also we have the s outside, so we forgot one thing, we have one s outside also, remember. So we write s here as well, so here s, and then we have minus ts over s square, ts plus 1 is equal to, now we have s here and s here and s square here, so it will cancel out. So limit s tend to 0, and becomes minus t over ts plus 1, simply. Yeah, because we have s here, s square cancels out, so minus t, right? So you put, now this is nothing but, if put s equal to 0 here, so you get minus t, so it's equal to minus t. Okay? So error is minus t meaning that output is less than the input. Yeah, so that's what it is. So this is the answer. Any questions so far, guys? Any question? Okay. We took long, little bit time in solving this, but the purpose was to, actually this is this demonstrates basically the whole chapter basically. Yeah. So rest we can talk about the methods. So okay, so the next question is 258. Okay, so let's go to number 2, and number 2 says consider unit step. So this is B52. Consider unit step function of unity feedback control system, both open loop transfer function is given by. So open loop transfer function is called a GS here, not TS. So let's say GS equal to 1 over S plus 1. Yeah. This is the open loop transfer function. Obtain the rise time, peak time, maximum overshoot, and settling time. Okay. So this state of, as you have seen in the lectures, these are derivation. We have done the derivation. You can just use that. So GS, this open loop transfer function. So you have to, this is unit feedback, you know. So first you have to complete the closed loop. Yeah, remember that. So we have like this, and like this is minus plus open loop negative feedback. Okay, so we have this one, right? And then you know that closed loop transfer function will be equal to simply GH over 1 plus GH. So you get that, and hence closed loop transfer function will be TS equal to simply 1 over S plus 1 plus 1. Yeah, and simply from here you will, what do you get? You get characteristic equation, which will be characteristic equation is equal to S square plus S plus 1. Yeah, this is the one you get, or you write equal to 1 over S square plus S plus 1, and that really means what? This is equal to S square plus 2 zeta omega n S plus omega n square, right? So this is how this one, and hence you know that omega n in this case equal to 1, and simply you can find out what the other things are. So anyway, so we have this equation, and from here we can find out what those values are. So we have S square plus S plus 1 equal to S square plus 2 zeta omega ns plus omega n square, and you know that omega n equal to 1. Yeah, and that also tells you 2 zeta omega n is equal to 1, and here omega n is equal to n, hence this gives you zeta equal to 0.5. So we have omega n here, we have a zeta here. So omega d you can calculate equal to omega n times 1 minus zeta square, and omega n 1 minus 0.5 square, right? So where omega n is equal to 1, so basically simply 1 minus 0.5 square equal to 1 minus 0.5, that's root 0.75. Yeah, so this is omega d. All other things are you can calculate based on the formula. State of the formula is the rise time. Let us say rise time. Okay, so this is TR. Okay, so you can use you can refer to your book or your the lecture notes. Okay, and here the rise time is simply is equal to pi, or simply this is given by 1 over, either you can write a pi beta over omega d, where beta is nothing but this is tan beta, where tan beta is equal to omega n root 1 minus zeta square divided by zeta omega n. Yeah, either you can write like this one, or you can write TR. So TR equal to 1 over omega d tan inverse omega d over minus zeta omega n. So you can also write like this. Yeah, so we can find out. The next thing is finding the peak time. Okay, so now peak time is this is a peak time. So TP, so TP is equal to pi over omega d simply, and omega d we have calculated already, which is omega n times root 1 minus zeta square. So you can find out that. Okay, so then overshoot and settling time. Overshoot, now overshoot is actually maximum overshoot. and this is calculated in percentage basically, right? So maximum overshoot. So in percentage we say NP equal to simply is equal to e to the power minus zeta over 1 minus zeta square pi. This is the value. Okay, multiplied by 100. So this is maximum percentage, because 100, this gives a percentage. Okay, and then settling time. Again, settling time, you can assume we are talking about the 5% criteria. So settling time, 5% criterion, and TS will be equal to 3 over zeta omega n. Yeah. Okay, this is how we calculate. Okay, so this is straightforward, nothing else. Okay, now next question is, any question, guys? 258. Okay. Okay, so B55. This about obtain the unit impulse response and the unit step response of unity feedback system was open loop transfer function is there. So again, those things in this is easy. So always whenever it is open loop transfer function is given, and when it is written that unit feedback loop, you have to always make the closed loop system first. Okay, so you have the GS here, and you know that it is talking about it has a feedback loop. So going like this, minus, this is plus. Yeah, go. So first we find out what is the closed loop. Always find out closed loop. Closed loop equal to GS plus 1 plus GS, and then you have to find out which is equal to CS over RS. CS over RS. Yeah, and then then you have to find out what is the value, the unit response of a unit feedback system was okay. So unit impulse response and unit step response. And then you have to find out for two cases. Actually, this is CT equal to what? When RT is equal to this is called impulse, right? So is a unit impulse, so you can say delta T basically, and RT equal to, this is number 1, number 2 is equal to UT. So this is what you have to do, right? So given the RT equal to delta T means this is impulse function basically, and this is RT equal to U2, and then you have to find out CT given this relation. So you can do it, right? So okay, any question, guys? 5, then 8. Referring the system in figure 575, determine the value of K and K such the system has a damping ratio of theta equal to 0.7 on damped natural frequency omega. So okay, so B58. So then it is referring to a figure. So first you have to find out what is the, so okay, so this I'll leave it on you, because I also want to solve here the Routh's stability criterion is needed. Okay, so basically in this case it's very easy. Once you find out the from the closed loop system, the figure, so you refer to figure 575. Okay, and then you find out what is the transfer function. So transfer function you will get something, let us say will be something like omega n square, or any value, let's call it A here. Yeah, and then you will get S square plus 2 zeta omega n plus S omega n square. In this form you will get, and from automatically you can find out here you have to find out the value of K such that omega n is equal to 4 radian per second, and then zeta is equal to 0.7. So in order to satisfy that, this is an inverse problem. So again, given omega n, of course, these values, zeta and omega n here will be in terms of k values. So zeta will be in terms of big K and small k, and omega n also will be big and small k. And you put this condition here and you can find out. So this will be equal to 4 radian per second, and this will be equal to 0.7. Right, and solve for big K and small k. Right. So from the figure, you find out the closed loop transfer function. So this is a closed loop. Okay. Once you have found out this, and then you bring it to in this this kind of form. And then omega n has equal to 0.7, so you put that equal to this, zeta equal to 4. And since omega and zeta both will have the terms k and a small k or big K, and hence you can solve it, you can find out the value. So this, okay. So 5.8 is done, 5.13. Okay. 5.13 you do yourself. It has what is the best speed response maximum overshoot. So you have to calculate the compare in terms of rise time. So B513. So basically there are three systems, three systems you have to compare, and in terms of a speed of response, so rise time. So you will have the TR and maximum overshoot. Okay, so overshoot M. So we write MP probably, right, for overshoot. Yeah, MP. Yeah, so you have to compare in terms of TR and MP, maximum overshoot, and the rise time. That's it. So that we know the equations, we can do it. 13 is done. Now 2021. So any question, guys? Okay, now now the Routh stability criteria we can use now for this onward. The B520. Okay, and it says determine the range of K for stability of a unity feedback control system whose open loop transfer function is this. So open loop transfer function is given as K and then S plus 1, S plus 2. Yeah, and the always you can write the closed loop. Okay, so always remember that we are going to use the closed loop system. I mean, unity feedback, it's given that this is unity feedback system. So we have to, so here goes like this, minus plus. Okay, so you can find out that the TS, which will be the closed loop system, will be K over 1 plus GS. Sorry, this will be GS over 1 plus GS. So TS will be nothing but K, and then we will have S plus 1, S plus 2 plus K simply. So this is the characteristic equation. When you say this is the one characteristic equation, right? So this is the characteristic equation. Okay, now once you have the characteristic equation, next thing will be to use the Routh. Excuse me, just a minute. Yeah. Okay. So we have the characteristic equation, which we know that we wrote it here. This. Okay. So S plus 1, S plus 2 plus K. So we have S plus 1, S plus 2 plus K, and we apply the Routh stability criteria. And for doing that, first we spell it out. So we have S, and then we have we can write in terms like S square plus 3S So we are multiplying this. So s square, and then we have 3s plus 2 plus k, right? We can write equal to we have s cube plus 3s square plus 2s, right, plus k, right? So this is our stability. This is the one which we have a characteristic equation. Okay, so this we have to use. So let's go on the next page, so that we will have a space. So s cube plus 3s square. So we can write like this. So we have we write s cube, and then we write s square, and so on, right? So we have s cube here, so we have 1, so we can also write here basically. So here we have 1, here we have 3, here we have 2, here we have 1. So first will be 1 and 2, and then 3 and 1. So 1 and 2, so 1 and 2, right, and then 3 and 1. So alternate, right? 1 and 2, 3 and 1. 3 and 1. Okay. Now we go further. So we have s, then we have 1 like this. Yeah. So here we go. We multiply this to this minus this divided by this. Yeah. This is how we prepare the table, right? So we go on. So we have 3 times 2. 3 times 2 is 6 minus 1 is 5 divided by 3. So we have 5 over 3. Yeah. And then for here, what do we have? We have 0, 0 here. So we get 3 times 0 minus 1 minus 0 divided by 3. So we get 0 only. So we get 0 here. Okay. Now here again, we have these multiply by 1 minus this divided by this only. So what do we get? 5 over 3 multiplied by 1 divided by 5 over 3. So we get 1. So simply, oh, sorry. So one thing you forgot. Yeah. So this is not, this is not 1, but this is k. Yeah. So 1, 3, 2, this is k, this is constant k. So we have to write k. So we made a mistake. So instead of 1, we write k here. Yeah. Okay. Now then the value will be different. So we have 3 minus 2 is 6 minus k. Okay. So let's correct it. So we'll have 6 minus k, right, over 3. Okay. So 3 times 2 is 6 minus k over 3, and this will be 0. Okay, now this is correct. Now this will be 0 because still this multiplied by this minus 0, the 0 divided by 3, so 0 is fine. Now next is this multiplied by this minus this divided by this, so we get simply k. So this multiplied by this minus 0 divided by this itself, so we get value k. So we will get k here. Okay. Now and here automatically this is also 0. Yeah. So okay. So the first row, if we compare here, that we have to compare. Now the problem says that we have to find out the stability. Yeah? So let's see what this is. Determine the range of k for stability of a unity feedback control system. Yeah, was open loop transfer function is given. So range of k we have to find out. Okay, so now how will we find out? So for stability, you know that they have to maintain the same sign. Yeah, and that means have to maintain positive in this case, right? So because we have 1 here positive, this positive, so all of them you want to be positive. Since these are positive, this also will be the positive only. So we have two conditions here. One has 6 minus k over 3 has to be greater than 0, and then k greater than 0. Yeah. So pure stability, we want strictly we want them to be strictly greater than 0. Yeah. So that really means what? from this one, it tells you what? This tells you 6 is, first gives you 6 is greater than k over 3, and this is k greater than k is greater than 0. And this tells you k is less than 18. So first one, so range, required range of k for stability is k is less than 18 and greater than 0. Yeah, so this is the answer. Yeah. Okay, so you see that these problems are actually easy problems, so what you need is understanding, so you can solve it very fast. Of course, problem depends on the problem as well. The main thing is the knowing the concepts. And in your quizzes also, the exam also, main thing is your understanding which will be tested. Yeah. Okay, so 450 already. Let us take one more question. Any confusion, any clarification you need, guys? 2021. So 2021, 23, 24, 26. 23, 24, and 26. Okay, so let's take one more, and others you can solve. So I will take 21 because this is again related to the Routh stability criterion. So since this is important, so take one more problem, this one. So this is on B521. Okay, and here we are talking about calculate the following characteristic equation. Consider the following characteristic equation, and the equation is this: S4 plus 2s cube plus 4 plus k s square plus 9s plus 25 equal to 0. Then using the Routh stability criterion, determine the range of k for stability. This is same as we did earlier, but this is the higher order basically. So we start with S4, and then we have S cube, S square, S, and 1. Yeah. So S4 is looking at here, we have 1 here. So we write 1, and then we have here 4 plus k. So say 4 plus k here, and then 1, 4 plus k, then 9 is there, and then this 25. So we write 25 here. Okay, so we have 1, 4 plus k, 25. Okay, done. Now next is this 2 and 9 here. Okay, so 2 and 9. So here 2 and 9. Obviously this means 0 here, right? Okay, so here we have to find out again the determine the range of k. Okay, so we start here. So we have this multiplied by this minus this divided by this. Yeah, so we have simply we can have 8 plus 2k minus 9. So 8 plus 2k minus 9 divided by 2. Okay, so 4 times 2 is 8, k 2k minus 9 divided by 2. We get that. And then the second one we get here is this multiplied by this 50 minus 0 divided by 2. So we get 2 times 25 minus 0 divided by 2 is 25 only. So we write 25 here. Okay, done. Okay, now next is so and not to forget, so this is the first row, this one is second row. Yeah, So like this, and we have 0 here. Yeah. So next is we are going to find out the value here, and this will be this multiplied by this minus this divided by this. Okay, this is complicated. So we write 9. So this multiplied by this. So 9, 8 plus 2k minus 9 divided by 2. So this is our 9 multiplied by this, right? And then minus 50. So we write minus 50 and divided by this value. So this minus this divided by this value itself. So now divided by this value. So 2 divided by 8 plus 2k minus 9. So we get one value here. So this multiplied by this minus this divided by this itself. Now second one will be this multiplied by 0. Yeah, and this also multiplied by 0. So we get 0. So we get only one value here. Okay, fine. Okay, and here we will get what? We get this multiplied by, so we have value 0 here. So again, our second value goes here, so not to be confused. Yeah, so our this multiplied by this minus this multiplied by 0 divided by this itself. So we get that this multiplied by this minus this multiplied by this, which is 0 divided by this, we get 25. So we get 25 value here. Okay, so it's complicated, but we will get some value from here. So main thing is this has to be greater than this has to be greater than 0, and this also has to be greater than 0. Okay, and this is being divided by this. We are already saying that this is greater than 0, so we can get rid of this. Let it go this side, So we get only this, which will be greater than 0. So meaning that our criteria will be conditions. We are or stability conditions, right? So we get first is 8. So let's write in different color. So first is 8 plus 2k minus 9 greater than 0. I am not writing divided by 2 because anyway, if it is greater than 0, divided by 2 is also greater than 0. So this is 0. And that simply tells us that k will be equal to greater than half. So k greater than 0.5. Simple. Okay, so this it goes 9 here, this side, and minus 8 is 1 divided by 2. So k greater than 0.9, 0.5. K greater than 0.5. Now from this one, what do we get? From this one. So again, this if we are assuming that this is greater than 0, so only we are looking for this value. Yeah, so we have second condition. Let's write different color, and that tells us that 8 plus 2k minus 9 is greater than 100 minus 9. How? The whole thing greater than 0, so this equal greater than 50, so just this equal to 50 multiplied by 2 by 9, right? And we get k, which is greater than 100 divided by 9 plus okay. Okay, so here 8 minus 9 is minus 1. So simply this 100 divided by 9 plus 1, so plus 1 and divided by 2. Yeah, and this this tells us that k has to be equal to 109 divided by 18. 109 divided by 18. Okay, so there are two conditions. The first condition says the k has to be simply greater than 0.5, and this tells us k has to be greater than 109 over 18, and which is automatically 0. Greater than 0.5. So only this is the range basically that it has to be this, so that the answer will be k greater than 109 over 18, and this will make sure that the system is stable. Yeah, any question, guys? Okay, always remember, guys, there may be some error or something, so when the process may be correct, but what I'm writing here sometimes may have error. And when have classroom teaching, that time students actually point out very easily. So please speak up when you see that there is something wrong there. Okay. Okay. Any question? Okay. If there is no question, guys, then I want to inform that I will post the homework. I could not do yet because I was on leave actually. So yeah, but I hope to post a homework this week. Okay. And I'm planning to have a quiz next week on Friday. Okay. During from 4 to 5. So I'm planning, I will inform you accordingly. Okay. So, and this will be based on what we have studied so far, means chapter 2, 3, and 5. Okay. Yeah. So any question? Anything? Okay. Okay, guys. Happy Diwali. Okay. And see you next week. Okay. Okay, bye.
Happy Diwali, sir.